Okay, in this video we're just going to go through some exam questions and we're going to walk through them. I've picked certain questions that are hard to explain on the PowerPoint, so I'm going to describe how we'd attempt them in real life. Okay, so this question is about sodium chloride and iodine. Describe the structure and bonding in sodium chloride. So sodium, if you look on the periodic table and on the back of that, in terms of ions, sodium forms a positive ion and chlorine is a non-metal, so it forms a negative ion. So we've got a positive metal, Na, and chlorine is a negative ion. So we've got a positive and we've got a negative. That means we've got ionic bonding. So that's what it's asking us about, because we're asking about a metal and a non-metal. So first thing we're going to say is that it will form a giant lattice structure. What I mean by that is we have that grid structure like a metal or a solid, which will be 3D, and some of those will be positive and some will be negative, and that will have that force of attraction in all directions, and that's your giant lattice structure. We're going to say that it will contain ions, so we're going to say it will contain Na plus and Cl minus ions, and that the ions are attracted by electrostatic force of attraction. So we can say there is an electrostatic force of attraction between Na plus and Cl minus. Okay, so worth 4 marks. We mentioned it forms a giant lattice structure. It's made up of ions, which is Na and Cl minus, and therefore there's an electrostatic force of attraction between Na plus and Cl minus, and that's the force of attraction in ionic molecules. Okay, the bonding in iodine is similar to the bonding in chlorine. Complete the diagram to show the bonding in iodine. Show the outer electrons only. Well, if you look at the periodic table, iodine is in group 7, which means it has 7 electrons in its outer shell, and it wants 8. So it needs 1 more. So these iodine atoms need to share 1 each, so they try and gain an outer shell of 8. So we're going to put 1 in the middle. I'm going to do dots and cross because 1 is from 1 and this one is from this one. So I need to get 7 crosses in total. I've put 1 in the middle, 2, 3, 4, 5, 6, 7, and then 1, 2, 3, 4, 5, 6, 7. And let's go around and double check. 1, 2, 3, 4, 5, 6, 7, 8. So it adds up to 8. That's 1 full outer shell. And this one, 1, 2, 3, 4, 5, 6, 7, 8. So by sharing 1 each, they effectively gain a full outer shell. And then it says, explain why iodine has a low melting point. Where you see the word low, you must think weak. Okay, something is weak about it because it's a low melting point, so it didn't need a lot of energy to overcome that force of attraction. So what we're going to say, it is a simple molecule. It's only made up of 2 atoms, very simple, and it has weak, there's that word, intermolecular forces of attraction between iodine atoms. Okay, so what this means, if we looked at it, we'd see these iodine atoms, okay, floating around, and between them they have these weak intermolecular forces of attraction between the molecules. So if you think at key stage 3, you had nice neat rows of atoms in a solid, then a liquid a bit further apart, then a gas really spread and moving around. So when we heat something up, we melt something and then boil it, we break these weak intermolecular force of attraction between the iodine molecules. We do not break the strong covalent bond here. So we're going to say they have a simple molecule, has weak intermolecular force of attraction between iodine molecules, which require little energy to overcome. Okay. Explain in terms of particles why liquid iodine does not conduct electricity. Well, in a covalent bond, there are no free electrons. To conduct electricity, I need something to be charged. So I need a positive or a negative. And with this one, if we look back at iodine, all of the electrons are in the shell and involved in the bond. I don't have any spare electrons. So what we're going to say is there are no free or delocalized electrons. So it cannot carry charge. Okay, it can't carry the electric charge because it doesn't contain any charged particles. Okay, so for something to conduct electricity, it needs to have a charge. Okay, on to the next question. Okay, this question is about diamonds. Draw a ring around the correct answer to complete each sentence. Diamonds are found in meteorites. Meteorites get very hot when they pass through the Earth's atmosphere, but the diamonds do not melt. Diamond has a high, low or very low melting point. It has a high melting point, one of the strongest substances we know. Most diamonds found in meteorites are nanodiamonds. A nanodiamond contains a few 100, 1,000 or million atoms, where it's 100, a few 100 atoms. Diamonds are used for cutting end of drill bits. Diamonds can be used for drill bits because they are hard, shiny or soft. We'll think about the properties going to be most useful for a drill. It will be hard. The figure below shows the arrangement of atoms in a diamond. So you can see here this 3D structure, and every single line here are covalent bonds. So there are no intermolecular force of attraction. They are all covalent bonds, so very, very strong. A diamond is made from what sort of atom? Is it carbon, nitrogen, oxygen? You should know that diamond is made of carbon atoms. And in diamond, each atom is bonded to 3, 4 or 5 atoms. It's 4. Okay, so each atom diamond is bonded to 4 other atoms. So each carbon forms 4 bonds, and you could keep going on like that, etc. all the way. The difference to that is something like graphite, which is made of carbon, but it only has 3 bonds. So diamond has a giant covalent, ionic or metallic structure. It's covalent because, like I said, all of the bonds are covalent. In diamond, all, none or some of the atoms are bonded together. They are all bonded, so it's a very, very strong molecule. Okay, on to the next question. Okay, so the diagram shows an atom of magnesium and an atom of chlorine. So here we see magnesium labelled up for us. It's got 2 electrons on the outer shell, so it must be in group 2. And chlorine, we can see here labelled up, and it's got 1, 2, 3, 4, 5, 6, 7 electrons in the outer shell, so that must be in group 7. Describe in terms of electrons how magnesium atoms and chlorine atoms change into ions to produce magnesium chloride, MgCl2. So it's asking us, how do these bond to form this product here? Well, let's first of all look at what that product means. What that means is we've got 1 magnesium and 2 chlorines. So how do they react to produce that? Well, first we have to think about what sort of bonding it is. Now, magnesium is a metal and chlorine is a non-metal. So the type of bonding that happens between opposites is ionic bonding. So this is an ionic bond with the metal forming positive ion and the non-metal forming a negative ion. Okay, so let's have a look at what's going to happen here. Magnesium's got 2 in the outer shell, so it's going to lose those 2 electrons and it's going to become 2 plus. And chlorine is going to want to gain them. Now it's not going to want to gain both of them, but it's only got 1 gap. So it can have one here, but then it's going to need another chlorine. We'll just do the outer shell. 1, 2, 3, 4, 5, 6, 7. It's going to need another chlorine to accept this other cross, this other electron over there. So that's why we're going to end up with 2 chlorine molecules, but it's got to accept the 2 electrons coming from magnesium over here. So let's write that down then in terms of our answer. So magnesium will lose 2 electrons in the outer shell, and chlorine will gain them. you need 2 chlorine atoms to accept the electrons from magnesium, as they will only take 1 each to make their outer shell to 8 electrons or full. Okay, so in terms of that, the key marks here comes from the fact it will lose 2 electrons, so that would have been a mark and that would have been a separate mark there. And we'd also got a mark for saying if chlorine will gain, that would have given you a mark. And they wanted you to know that you would need 2 chlorine atoms to accept them. So that's where your marking points came from. Okay, on to the next bit of this question. Calculate the relative formula mass of magnesium chloride. This is an easy question, I just want to add it up. So it's given you the atomic masses and we want to find the formula mass, and it's given us the formula here. So if magnesium is 24, I've got 2 chlorines and they're both 35.5, so we just add up those numbers. So we've got 24, add, brackets, 35.5 times by 2. So if you do it in that way, the examiner can see exactly what you've done to get the answer that you need. So in this case, we've got 24 added together to make 70. So 35 and 35 is 70, plus the 0.5 is the 1. So we've got 24 add 71, which overall is going to give us, we get 95. So 95 is our relative formula mass. Okay, on to the next question. Okay, now to the next question. Magnesium reacts with steam to produce hydrogen gas and magnesium oxide. The equation for the reaction is, so we've got Mg with an S, which just means solid, plus H2O, which is gas, MgO, which is solid, plus H2, which is gas. The teacher used 1 gram of magnesium. Use the equation to calculate the maximum mass of magnesium oxide produced. Give your answer to 3 significant figures. So if you are asked to calculate mass, this is the method you are going to use. You first will look at what it's given you and what they're asking you to find out. So it's telling us we used 1 gram of magnesium. So this is what we're looking at. So we had 1 gram of magnesium. It's asking us to calculate the mass of magnesium oxide produced, which is this over here. Okay, and it hasn't mentioned either of those two, so I'm ignoring them completely in the equation. I'm now going to put magnesium and magnesium oxide as my headings on down here so I can work underneath. So what I know is I want to know if I used 1 gram of that, how much would I get of here? So I need to have some sort of figures I can compare in terms of masses, and because I only know that in terms of grams, I'm going to use atomic masses to compare. So what this means is if I had 24, okay, atomic mass of magnesium, then over here it would be 24 plus 16, 24 and oxygen is 16, okay, which will give me 40. So what that's saying is if I had 24 grams, it would give me 40 grams, but I don't, I have 1 gram. So if I want to get this side to be 1, if I wanted 1 gram, I'd have to divide that by 24 to give me 1 gram. So I need to do exactly the same over here, divide that by 24, which will give me 1.67. So that is my answer. So it's nice and straightforward, it's not difficult. So do practice these calculating mass questions because they're easy if you just circle the bits you want and cross out the other bits and then use your columns to work underneath. So it tells me the teacher's demonstration produced 1.5 grams of magnesium oxide. It didn't get 1.67. Use your answer from the part above to calculate percentage yield. It does also say if you couldn't answer that bit, it's given you one to use instead as the maximum mass. But if not, then use this one because this is going to be the correct answer. So to find percentage yield, that would be like 100% what we should have got. We didn't, we only got this. So it's 1.50 divided by 1.67, which gives me 0.89. And I need to times that by 100 to make it into a percent, which is going to give me 89.8% or 90. So I'm just going to put 90% then, round that one up. Okay. Then it says, give one reason why the percentage yield is less than 100%. Well, we've talked through these, so we could say that it was a reversible reaction, would have been absolutely fine, as the answer there. We could also said that some of the magnesium oxide may have been left in the tube, or it might have been lost. We could also have said we had a different or unexpected reaction that we didn't know we were going to get. Okay, so several different answers we could have had to that one. Okay, on to the next question. Okay, this question is about iron and aluminium. Carbon monoxide reduces iron 3 oxide. Fe2O3 plus 3CO goes to 2Fe plus 3CO2. Calculate the maximum mass of iron, so iron is there, so that's what we're trying to find, that can be produced from 300 tonnes of iron 3 oxide. So iron 3 oxide is there, so we've got 300 tonnes of that, so it hasn't mentioned that and it hasn't mentioned that, so we're going to ignore that altogether. So again, we're going to write down, so we're clear of what we're trying to work out, the bits on our lines. Okay, so again, if we've got 300 tonnes of this, we want to find out how much we're going to make of that. I know tonnes sounds like a big number, just ignore it. It could be grams, it could be kilograms, it could be anything, but they've just chosen to do tonnes. So again, we don't know the masses, so we're going to start with atomic masses and work from there. So let's work out the formula mass of each of these. So Fe is 56, so we've got 56 times 2, add 16 times 3, so we've got 3 lots of oxygen. Then over here, we've got 56 times 2. Okay, so this here on this side equals 160, and on here that equals 112. So if I'd had 160 grams or tonnes, that would have been 112 grams or tonnes. But we don't, we've got 300. So what do I need to do to 160 to get to 300? Well, let's divide 300 by 160, and that number gives us 1.875. So 160, to get to 300, I have to multiply 160 by 1.875, and that will get me to 300. So I need to do that on this side over here. So I need to do 112 times 1.875, and that will give me 210. So if I've got 300 tonnes, I will get 210 tonnes being produced. Okay, right, on to the next question. This question about carbon and gases in the air. Sometimes carbon reacts with oxygen to produce carbon monoxide, or CO. Calculate the relative formula mass of carbon monoxide. So this is just adding them together to find the formula mass. So carbon monoxide is just C and O, so that's 12 and 16, which gives us 28. Okay, nice easy one there to carry on with. Calculate the percentage by mass of carbon in carbon monoxide. So what that's saying, if we had all of carbon monoxide is 28, how much of it is carbon? So carbon is 12, and carbon monoxide, so that's 12, and carbon monoxide is 12 to 28. So we do 12 divided by 28 times by 100, and that will give us our percentage mass in this question. Okay, so 12 divided by 28 times by 100 gives us 42.9. So that is our percentage of carbon in carbon monoxide, 42.9%. The rest of it is oxygen. Okay. This question is about compounds. Balance the equation for the reaction. So let's have a look how many atoms we've got on both sides. So I do this as a table, but you might do it in your own way. I'll try and write it on this side here. So first thing, I had look at all the atoms you've got. So you've got lead, oxygen, hydrogen, nitrogen. Okay, and then I do a table before and after the arrow, so I can look at how many atoms I've got present. So there's one lead before, one lead after. Oxygen, I've got 1, I've got 3 there, that makes 4 together. Oxygen's on this side, I've got 3, but that's multiplied by 2 outside the brackets, there's 6, plus 1 there, that makes 7. Hydrogen, I've got 1 on this side, but on this side I've got 2. And here I've got 1 nitrogen and 1 there, but again it's inside brackets multiplied by 2, so you've got 2 there. Now I need to balance. So lead is fine, that's all balanced, but these are not. So the oxygen, the hydrogen and nitrogen are all lower on this side than they are on that side, and they're all present in this molecule here. So I need to double my nitrogen, double my hydrogen. I need to go with my oxygen from 4 to 7. So if I put a 2 on here, what I've done is I've changed the hydrogen now to a 2 on this side, the nitrogens to a 2 on that side. The oxygens here is a 6, so 2 times 3 is 6, but that one there makes that to 7 overall. So that's a 7, that's a 2, and that's a 2. I am now balanced. So it gives a total number of atoms in the formula PbNO3, 2. So you just need to add all of the atoms up there. So you've got 1, 2, and then you've got 6 oxygens in total, and you've got 2 nitrogens. So we've got in total here, we've got 6 oxygens plus those 2 nitrogens, that makes 8, plus the lead, that makes 9. If it's easy, you can write it out if you can't visualize it. So 1 lead, you've got the 2 nitrogens, and you've got the 6 oxygens. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7, 8, 9 atoms in total. Okay, on to empirical formula. So an oxide of lead does not have the formula PbO. It contains 6.21 grams of lead and 0.72 grams of oxygen. Calculate the empirical formula of this lead oxide. It's given us the relative atomic masses, and it says you must show working to gain full marks. So if asking for empirical formula, you need to learn SMADR. Okay, and hopefully you've been taught this way before. So what you do is you write SMADR down this side of your lines, and you work neatly to work out what our ratio is going to be. So let's talk through what this stands for. S stands for symbol. So that's the symbols we are going to use in our formula at the end. So it's told us we've got lead oxide, so lead and oxygen. So our symbols are going to be Pb for lead and O for oxygen. Spread them out so you've got space to write underneath. M stands for mass. So the masses are 6.21 grams of lead and 0.72 grams of oxygen. Okay, double check you get the right numbers down, because if you get them down wrong at this stage, it's going to knock everything out underneath. A stands for atomic masses, which are there. So lead is 207 and oxygen is 16. D stands for divide. So we're going to divide the two numbers above just as they're shown. So 6.21 divided by 207 and 0.72 divided by 16. So that's our two divisions we're going to do. This gives us an answer of 0.03 and this one 0.045. A stands for answer divided by the smallest. So what is the smallest number here? It's this one here. So we're going to divide those two numbers by the smallest, because with a ratio we want one of them to be 1, so we've got a comparison. So we're going to have 0.03 divided by 0.03, which is going to give us 1, and then 0.045 divided by 0.03 gives us 1.5. Okay, now in this case we can't have 1.5 of an atom, so you can't do O with a 1.5. We need to double that up to get that to 3. So if we're doubling that one, we need to double this one. So this will be a 2 and a 3. R stands for ratio. So our ratio is PB2. So the 2 and the PB go together, and the oxygen and the 3, so O3. So the empirical formula is PB2O3. So if you use SMADR, it's really, really easy to structure your answer. Okay, scientists separated the compound from the maple syrup. This compound contained 5.65 grams of carbon, 2.20 grams of nitrogen and 0.629 grams of hydrogen. Calculate the empirical formula. So again, think SMADR as our symbol to help us remember. So I'm going to write that down the side of my lines, and I'm going to use that as my guide. So S stands for symbol. Let's go in the order they've given us, because that's how they're going to want the formula. So carbon, nitrogen, hydrogen. Spread it out so you've got plenty of room. Masses, 5.65 grams of carbon. Please double check all your numbers line up correctly. 2.20 grams for nitrogen and 0.629 grams for hydrogen. A is for atomic masses. So carbon, check, because it's not in the right order here, is 12. Nitrogen is 14 and hydrogen is 1. D stands for divide. So we divide them in the order shown. 5.65 divided by 12, 2.20 divided by 14, and 0.629 divided by 1. So work those out on your calculator, and what you should end up with, and keep them to 3 decimal places, I would, because otherwise if you round them up too early you'll get the wrong numbers. So here you get 0.471, 0.157 and 0.629. Answer divided by smallest. The smallest number we've got here is 0.157. So all these numbers are going to be divided by that. So 0.471 divided by 0.157. 0.157 divided by 0.157. And 0.629 divided by 0.157. So that gives you as your ratios 3, 1 and 4. So your empirical formula is carbon 3, N 1, we don't write the 1, and H 4. Okay, funny looking formula, but that is this ratio of atoms, okay, that we get in the empirical formula. So that's the correct answer there. And then on to another one about empirical formula. This question about copper. Copper can be extracted by smelting copper-rich ores in a furnace. The equation for one of the reactions is in the smelting process. So you've got the equation here for you. A compound in copper ore has the following percentage composition by mass. So 55.6% of copper, 16.4% of iron, and 28.0% of sulfur. You just take the percentages as the mass. So imagine they were out of 100 grams, that would be the masses. Calculate empirical formula. So let's write SMADAR, S-M-A-D-A-R, as we go through our order here. So S stands for symbol. So as we go along, we've got S, and we've got copper, so Cu. We've got iron, which is Fe, and we've got sulfur, which is S. Masses, 55.6 for copper, for iron 16.4, and for sulfur 28.0. Then if we go on to atomic mass, A, for copper, check along the line, make sure you've got the right one, 63.5, for iron 56, and for sulfur 32. D for divide, do we do 55.6 divided by 63.5, 16.4 divided by 56, and 28.0 divided by 32. Okay, and then we jot those numbers in, try and space them out a little bit more than I've done. As you can see, I'm struggling now for space on my work, and I do really recommend you showing exactly what you've done. I know it's a long, lengthy process, but look, it's worth 4, maybe 5 marks in the exam. It's well worth making sure you spend some time on it. So these calculations here, 0.875, remember don't, or 876, sorry, the calculator, make sure you don't round up too early, give it to a good 3 decimal places. This one here, 0.293, and finally this one comes out as 0.875. Okay, so answer divided by smallest, that's your 0.2. So we've got 0.876 divided by 0.293, 0.293 divided by 0.293, and finally 0.875 divided by 0.293. Okay, that gives us a ratio of 2.9, 1 and 2.9. Obviously you can't have a point for an atom, so you just round that up to the nearest number, and in this case we're not going to double it because it's not a half, it's almost a full number, so I'm going to have that as 3 and that is 3. Okay, remember it might, because you've rounded up a bit early, you might not get it exactly right down here, and that's absolutely fine. So empirical formula then is Cu 3, Fe 1, so we just write Fe, and S 3. Okay, so that's the empirical formula. So if you get an empirical formula question, actually, you should be quite excited about it. If you're using SMADAR, it's dead easy, and it's worth potentially 4, maybe even 5 marks. Okay, so that's the example questions for C2, and hopefully they've been of some help to you.